Before we continue on with the history, let's jump forward in time a little bit and talk about the proofs, the other proofs of the heliocentric model. We have the phases of Venus that proves the heliocentric model. Well, we had this discussion, you can't prove something to be correct, but that's one big hurdle the heliocentric model was thrown up against and passed. Two others are so here we are with proofs. Heliocentric model. Two others are the aberration, let's see, it's two R's, aberration of starlight, which is kind of a tricky concept. I'll try to explain it though, mid-1700s. And the other is a kind of easier concept to wrap your mind around, and we'll be using this concept tremendously throughout the course, and that's stellar parallax, or parallax of any type. And this came in about the mid-1800s. And the times at which these tests were done were driven by the technology. You needed telescopes of sufficient quality, measuring devices of sufficient quality to see these two things. So aberration of starlight, let's start with that. And here's an analogous situation. Suppose you're sitting in a train and it's not moving, and you're looking out the window and it's just raining down from above. The wind's not blowing it sideways or anything. And you'll see the drops, the rain coming straight down. If the train starts to move, it looks as if the raindrops are coming from the forward direction, from the direction in which the train is moving. You've all seen this before. If you're a train or a car, if you're moving and it's raining, the rain, or if you're running in the rain, you get soaked on your front, right? It's like the water's coming from the forward direction. It's really not. You're moving into it, but there's this appearance. So let's consider it with the case of light. So here we have a star, and it has to do with the light travel time, the fact that light takes time to actually move through space, at least over vast distances, it takes time. So here we have the Earth, and it's moving through space in this figure to the left. This is modified from your textbook. I didn't like the one in the textbook. And we have some star out there, and the light is coming from the star down to Earth. Now, from our point of view, we're not really feeling our motion through space. You only feel accelerations and decelerations, as we'll find out when we talk about Newton. But if you're just traveling at a certain speed, you don't really feel it. But here we are on Earth, not feeling it, so we like to think of ourselves as not moving and other things out there moving. And you really can't tell in space, am I moving, is that moving? Am I standing still, is that standing still? That's actually the foundation of Einstein's theory of relativity, which take 102, we'll come back to it. But without elevating it too much, imagine Earth is sitting there and the star's moving in the opposite direction at the same speed. Well, what would we see? Since that light takes a while to get to us, if we're seeing light coming from the star, say the star is right here, right now, and we're down here, the light that we're seeing isn't coming from the star at this position, it's coming from the star at this position, where the star was when it released the light. It then has to travel through space to us. So the star is really here, but because of our motion in this direction, it appears to be coming from the forward direction by about 20 arc seconds. That kind of make sense? I'll try to demonstrate it. Usually I bring in like a Nerf football or something, but I forgot. So let me get this right in my head here first. Okay, so over there somewhere, I'm not going to pick someone because then I'll miss you and feel stupid, and I don't know how far this styrofoam ball is going to go anyway, but wherever this lands, that's Earth, okay? And this is light. I'm going to throw the light. I'm a star, and we'll do it kind of from the point of view of the second diagram where Earth's sitting there and the star's moving. So I'm moving along, I throw it, and you catch it. Now, at this moment in time, I'm right here in line with you, but where'd that ball come from? Over there, right? Now, in reality, I'm not moving this way. You're the Earth. You're moving that way. So if you're traveling through space, the things on your sides don't appear to be coming from there. They appear to be coming from a little bit forward. Sound good? Can I have my ball back? Whoop. It's okay. It's hard. These things don't go very far. Okay. That's aberration of starlight. And it's an interesting effect, and spacecraft, when they're up there, they often position themselves with respect to the stars. It's something you got to take into account. It's a pretty big effect, 20 arc seconds. 1/3 of an arc minute. And that's a big effect astronomically. Stars, if you look through a telescope, they appear to be about an arc second across due to atmospheric blurring or due to the quality of your telescope. This is 20 arc seconds. This is a noticeable shift. And it's always the stuff at the side. So suppose I'm Earth and I'm going around the sun. So if I'm going in this direction, everything over here has been squeezed forward. And up here too. Squeezed forward, and down here, squeezed forward. It's like the whole sky is squeezed forward. Here, 20 arc seconds, and less and less and less until you get to the star directly in front of you. And as I move around the sky, or move around the sun, now it's these stars over here that are squeezed in that direction. So it's different stars, they're changing their position. It's kind of weird, the effect. As you're moving, the apparent position of all the stars is pushed into your forward direction. As I come around the sun here, they're all pushed that way. So the point I'm trying to get to, in a heliocentric model, you would expect this very weird effect, where all the stars in your direction of motion, or all the stars around you are pushed into your direction of motion by an amount that depends upon your speed of motion around the sun. And it's always changing as you're changing your direction. And of course, in the geocentric model, you're not moving, so you wouldn't expect this effect. In the heliocentric model, you expect this really weird effect, and that's exactly what you see. It took until the mid-1700s to do it. 20 arc seconds, and back in, Galileo could measure 20 arc, Galileo could see different stars, he could measure their distances between them. You can measure 20 arc seconds. The reason this is a little challenging is if I'm going this way, every star over here moves forward 20 arc seconds. It's not like just one of them does, and I can measure that with respect to the rest. They all do, so I have to measure it with respect to the stars over there. To measure 20 arc seconds over a 90-degree angle is a little bit more challenging than measuring 20 arc seconds compared to stars around it. Know what I'm saying? So it took until the 1700s to be able to make that kind of measurement, saying, well, all the stars here are actually shifted in that direction by this pretty big amount. Okay, that's aberration of starlight. Then came stellar parallax, and this was the nail in the coffin of the geocentric model. Now, by now, everyone's pretty much accepting of the heliocentric model by the mid-1800s. But here's parallax, a big concept in this course. This is stellar parallax caused by the Earth going around the sun. So here's the sun, here's the Earth going around it. And suppose we're looking at a nearby star, and these are faraway stars. They're really off the top of the figure. So if I'm standing here looking at this nearby star, it would appear to be over here in the sky. But if I wait 6 months and come around and look at it over here, it would appear to be over here in the sky. And so the position of the nearby star shifts with time with respect to the background stars, and then it shifts back. So over 6 months it moves in this direction, over 6 months it moves back in that direction. And then it repeats over and over as we go around.
And we'll demonstrate that right now with our fingers. I think we did something like this with Stonehenge. But let's do it again. So you're going to grab a finger, preferably your own finger, and put it in front of your face real close. And close one eye, and notice where the finger is blocking the wall behind me. Then switch the other eye. And you see that it changed position. A big amount. That's parallax. If I measure that angle that it shifts, and I know the distance between my eye, I can calculate the distance between my eyes and the finger. Now put your finger as far away as you can, without taking your hand off, and close one eye, and switch the other, and you see the shift is smaller. Big shift, small shift. And you can see it here in terms of the angles. If, in this picture, I think it's a pencil, not a finger, but if you hold the pencil close, it's a big angle between your eyes and the pencil. And so you notice a big shift. But the farther away you make it, the skinnier this triangle gets. And so it's a smaller shift. And eventually, you can consider stars that are very far away. And the shift is going to be very, very small, hard to measure. Well, the nearest stars, the magnitude of the shift, so aberration of starlight is 20 arc seconds. Stellar parallax is less than 1 arc second. It's about 1 arc second for the closest star, Alpha Centauri. But quickly, as you get farther out, it becomes less than an arc second. And an arc second is about this, as I said, if we take a picture of the sky under good observing conditions, the atmosphere blurs the image, as we'll talk about later, to a scale of about 1 arc second. So most of these parallactic shifts are smaller than the size of the star in your image. You basically have to centroid it and try to measure the shifting center. And it's only going to work for the nearby stars, at least with the technology of the mid-1800s. But by that point in time, they could do it for the nearby stars. Since then, the technology has gotten better. We measured parallax to the nearest 1,000 stars, the nearest 1,000,000 stars. And we're only a few years away from being able to measure parallax anywhere in our galaxy. And it's about 100 billion stars. Again, it's just how good is your technology? How good is your telescope? How well can you centroid a star? And most of this is done from space now, so we don't have to worry about the atmosphere blurring it and making it more difficult. Anyway, by the mid-1800s, they measured stellar parallax to the nearby stars. And again, in a heliocentric model, that's fine. In a geocentric model, how much stellar parallax do you expect? None, because the Earth is not moving. Here it's moving, and indeed we see the effect. The stars, I mean, they've been looking for this ever since Greek times. It's just back before the telescope and before the telescope was advanced. The stars are just so far away, you can't measure the parallax with that technology. So it was an argument for the geocentric model, the lack of parallax for all those years. We don't see any parallax. We should see parallax. But in reality, the stars are just much farther away than people had ever anticipated, and it took a long time to find it. Okay, any questions about the death of the geocentric model? When I released it, I was throwing it straight, but I was moving, and so it kind of went on a diagonal. So you saw it coming from there, even though I'm over here now. Make sense? So go ahead and get the ball. You probably, it doesn't throw very well, so. Nice throw. Have you thought about trying that for the basketball team? Somebody owes me a cup of tea. Okay.